Okay. Now, the next problems are a little different. Thankfully, because my brain's a little fried with the calculator. How about yours? Okay, so let's look at this. How is this different? Oh, this has number 4 and number 5. I don't think that was supposed to happen. Number 4 is kind of short and sweet, isn't it? Given the same reactant concentrations, the reaction of carbon monoxide plus chlorine gives us COCl2 gas at 250 degrees Celsius. It is 1.5 times 10 to the 3. That's known as what, 15,000? Yeah, times faster, or times as fast as the same reaction at 150. So we've increased the temperature by 100 Celsius degrees. That's a whole bunch of doubling, isn't it? So what do they want me to do? They want me to calculate the activation energy for this reactions. All right. Now, these kinds of questions are asked by AP a lot. Something is as fast as, those sorts of things, which is going to force you to assign a value of 1 to somebody. So since this is a higher temperature than this, I would say that 1 is assigned to the 150 situation in degrees Celsius, and the 1.5 times 10 to the 3 times as fast as then is your multiplier. So what we're going to do now is actually put that in, but we got to convert these temperatures to Kelvin and make reciprocals. We're going to get a perfect R when we do this. So EA is still equal to minus the energy R times the slope. So I've just got to think about what I'm doing. L1 is going to be my temperature. Okay, so I want 1 over T in L1. And L2 is going to be ln of K. So I'm going to assign this K of 1, this K of 1.5 times 10 to the 3rd. This temperature was 150 plus 273. This one is 250 plus 273. So let's see how that looks in the calculator. Clear all my lists. Starting over here. So I don't make any errors. I'm going to do 150 and 250. Go to the top. I'm going to take everything in L1. I'm going to add the 273. I'm going to add the 0.152. And then I'm going to take the reciprocal. There. Okay, then I'm going to come over here, and I'm going to put in 1 and 1.5 second EE3. Then I'm going to take the natural log of both. Oops, didn't mean to hit second. Well, ln. There we go, of second 2 for L2. And there I have it. That's going to be a perfect slope, isn't it? It's going to have a perfect R because 2 points defines a straight line. So we're going to have a perfect linear regression on this data. I'd prefer a third piece of information, but it is what it is. So if I run the linreg on this, stat, calc, for, enter, there's what I end up with. Very nice. Notice the perfect R. So the slope is going to be equal to negative 8.31 times the negative 16189.3 yada yada yada. Alright, so that means that I'm just going to ignore those negative signs. 8.31 times 16189, if I wrote it down properly, is going to be equal to 134.5. Let's call it 135. 135 kilojoules per mole for the activation energy. And what is the value of K when the temperature is 100? So you know X, agreed? It's an X value, and 373 is what it will be in Kelvin, and we need to take that to the -1. So I go to my graph, which is still set up at 1L2, but it's got the wrong stuff in it. I don't think I pasted. Checking something real quick. Okay, so I'm going to go ahead and paste that, run it again and paste it into Y1. There. Now it's actually pasted in there. So leave that one alone. And I'm going to take this out. Clear? Okay, so now if I go zoom 9, there we go. Go figure, a perfect straight line through 2 points. Okay, so now I go second trace, and I know what x is. It's 373, but don't forget to take the reciprocal. And I got to go 2. Because I'm way outside my range. No? 150, 250. Yeah, my range is smaller. Okay, so zoom 3 to zoom out. Enter to make it happen. Repeat. Second. Calculate. Enter. 373. Don't forget to take the reciprocal. There we go. So y equals ln of k, it's baby k, equals negative 5.14, but remember it's stored. Therefore, k equals second quit, second ln. Get that y value by going alpha 1. And we get 5.83 times 10 to the negative 1, 2, 3. 5.83 times 10 to the negative 3. And amazingly enough, that is a correct answer. Welcome back. This is a continuation of the Arrhenius Made Easy handout. We've got a couple more problems to work. This particular one is from the Witten-Davis-Peck chemistry book, and it was 5th edition. It was number 51, and it's just been adapted by yours truly to make it a little more meaningful in the context of AP problems. So let's give it a shot. Biological, actually this one doesn't need a calculator, we can make this bigger. Biological reactions nearly always occur in the presence of enzymes as catalysts, and the enzyme catalase, which acts on the decomposition of hydrogen peroxide, reduces the activation energy for the reaction from 72 kilojoules per mole, which is uncatalyzed, to 28 kilojoules per mole when it's catalyzed, both at 25 degrees Celsius. The total delta E for the reaction is negative 204 kilojoules per mole. Write the balanced chemical equation for the decomposition of hydrogen peroxide. All right, any of you in AP Biology already had it, currently in it, going to take it? Well, this is interesting because Lab 2 is this exact reaction, which is catalyzed with this exact enzyme using potassium permanganate, so it wraps this concept together with redox titrations. And so it was one of my kids' favorites because often they'd had AP Chemistry as a junior and came back for AP Biology as a senior. So we start with our H2O2 in the liquid form. You wouldn't have to put that, but, you know, I'm doing it for good form. And we're back to that brown bottle. It's a brown bottle because light catalyzes this reaction. And the trouble is we have to store it in a brown bottle because it's going to decompose into water. Okay, that's just annoying because who wants to go buy a bottle of peroxide to end up with a bottle of water? But the trouble comes in that it's also going to make oxygen gas. That's where the danger comes in, because that could explode your bottle and make quite the mess. All right, so easy enough, starting off with just a good balanced equation with light catalyzing that normally, but in this case they told us we're going to actually use an enzyme called catalase. ACE endings that you may recall from biology for enzymes. Draw and label a reaction coordinate or potential energy diagram. I know. It's just grown-ups that can't get along. I don't know why we have to have so many names for everything. But indeed we do. So I'm just going to make myself a nice big... I'm going to do it this way. Yeah, that's probably better. A nice big... Well, that didn't work. Undo. Let's try one more time. There we go. A nice big energy coordinate diagram. All right, also called potential energy diagrams. All right, so let's say, what do we got going on here? Basically, if we're going to lower the energy, we know that we've sort of started out something like this on this diagram, so I'm just going to give that a shot and see what we've got going on. So this is my H2O2. this is my H2O plus oxygen gas. I'll do that this time for a gas. This is the sort of thing they want me to do. And they did tell us an overall delta E. Go back up here and find it. The total delta E was a negative 204, and the reason it's negative is because we're starting out with a lower, or ending up with, I should say, a lower energy set of products than we started out with higher energy reactants. 204 kilojoules per mole of reaction. And then, what else do we know? We know that uncatalyzed, this value, the EA was equal to 72 kilojoules per mole, while if I come in and catalyze this, cutting that down by about a third, or down to about a third, I should say, cutting it by 2/3, so that this new one, this is not drawn to scale, obviously, is equal to, what did they say, 28? 28 kilojoules per mole. Just a matter of seeing if you know where things go and if you can interpret these diagrams. You also should realize there's an activated complex or transition state of sorts up there. And I think I left everything pretty much intact. So what is the activation energy of the uncatalyzed reverse reaction? So we're going to start here at the H2O2 and O2, and we're going to follow that back over this direction. So that means we need to take our 204 total delta E over here, which will get me, again, from here to here. We need to add to it that other 28 that's necessary for the climb, and this is all in kilojoules per mole. And I think that is 4 plus 2 is 12. I mean, 4 plus 8 is 12. I had 2 in my head. Carry my 1, 3. Isn't that 232? Oh, it says uncatalyzed. Oops, it's not 28. Sorry, that's 72. Okay, so that's going to be 6 and 7 and 2. 276 kilojoules per mole. The un part got me. And then what is the activation for the catalyzed reverse reaction? Now I've got my 204 again. This time only 28. And so that comes out to be my 232 kilojoules per mole. Good multiple choice type questions. Good basic concepts. Nice if it's a kinetics issue, a kinetics piece of the AP exam that comes without a calculator, because the numbers were fairly easy and I could do it without a calculator. How about that? Imagine. All right, let's move into the final one of these puppies and see what we can do next. So this one is adapted. I am going to need a calculator for this one, I know. And there it is. So this is adapted from the 2004 exam. It was number 6. Oh, no, I made it number 6. I don't remember what number it was. It might have been number 2 or 3, because you definitely had a calculator with this. But we already know we're in trouble when we see question marks in a data table, right? So we really only have, we have 3 sets of data if we use absorbance and time, but we only have 2 sets of data if we use molarity and time. That would automatically give us a perfect straight line, so that's not a good plan. We need to go with more data points. We also could solve for that molarity using Beer's law. Beer's law is what relates an absorbance to a molarity, and hopefully you've done a lab that had a portion of Beer's law in it. If you haven't, you should, and then this will make more sense to you. I'm really hoping you did one out of the Laying the Foundation series of stuff in first year, where we use It's Not Easy Being Green, and we do nickel chloride, which is a really pretty green. And we teach you Beer's law with that and give you an unknown, and it's kind of fun. Okay, so let's read this puppy. The following data was collected during the decomposition reaction of a colored chemical into species X into colorless products. Monitor with a spectrophotometer. You might have used a colorimeter in class. By measuring changes in absorbance over time. The reaction was carried out at 25 degrees Celsius, 1 atmosphere pressure. Species X has a molar absorptivity constant of 2.75 times 10 to the third centimeters per centimeters per molarity, and the path length of the cuvette is 1.0 centimeters, and the data for the experiment are given in the table below. So you knew one of these question marks is going to be filled in right off. So calculate the initial concentration, that's code for molarity, of the colored species. Well, I'm a fan of Beer's law being stated as absorbance equals epsilon for molar absorptivity constant, L for path length, because L and length make sense to me, C for concentration and molarity. But the AP exam put this on the formula sheet, which I'm not as familiar with, but either way you look at it, I am solving for C. I have been told what A or epsilon equals, which is that 2.75 times 10 to the third, and I have been told what L or B equals. So you choose your form that you like. Either way, we're going to solve for C, which is concentration in moles per liter. So that is A over AB. The A's get confusing, which is why I'm not a fan of that format. So the absorbance is 0.330 right off the table. The A is 2.75 times 10 to the third centimeter molarity. Make that a little deeper. And 1 centimeter. So guess what? Centimeters cancel. A 1 over molarity is molarity, and that's good if you're solving for concentration. So C equals 0.33 divided by, open a paren. Really, I didn't need to because I'm not going to bother to multiply that by 1. I just could have multiplied that denominator by 1. It's pointless. Why waste the energy? So that comes out 1.2. Missed my decimal. Times 10 to the minus 4 molar. 1.2 times 10 to the minus 4 looks very nice in that table, because that would be 12 times 10 to the minus 5 if you wish. Okay, so use the data given for concentration. That's why I let the problem lead you. They just had you solve for concentration so you could use it, and time to determine the order of the reaction. Well, that makes it concentration, time, data, and dun, 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 you're in the land of integrated rate law, and justify your answer. So, do I have room to write here? Not so much. But let's clear this, and let's set this up. This is integrated rate law, so I want L1 to be my time. I want L2 to be my molarity. I want L3 to be the natural log of that molarity. And I want L4 to be the reciprocal of that molarity. So away we go. Clear your lists if you have not already. I did already. So now I'm going to put in time. Even though time's way over here, I want that to be L1. So 0, 10, 15. Not very many data points. Well, dadgummit. 10. Okay, 0, 10, 15. Typing correctly is nice. I'm going to do the shortcut and go 12, 6.25. As time goes by, they already told me this stuff is disappearing, so these numbers make sense. And 3.5. 12, 6.25, 5, 3.5. Didn't need that one. That's going to cause an error later. Clear that one out. Delete. Okay, that whole shooting match, up to the top, all the way up to the top, needs to be taken to EE5, minus 5. So second L2, second EE to the minus 5 was just faster than typing all that in by myself. Okay, so what's going to happen with L3? Let's go ahead and set that up to be the natural log of everybody in L2. And L4 is the reciprocal. Alright, so now I'm ready to get down to it and run these linear regressions and figure out the order of this reaction. Remembering what I'm graphing, right? I know, you've listened to it already, and hopefully this is getting really monotonous, and you're fast-forwarding as I speak. Time, 0, 1, 2 for the orders. 0th, first, or second. This would be concentration. This would be Ln of concentration. This would be reciprocal concentration. That's what I'm about to do. Whichever one gives me the best R value is the best straight line and determines the order. So off to the races. second quit, stat, calc, linreg is number 4, second, I don't think it's second hit, second 1, comma, second 2, comma, go get your y equals however you like. Trying to beat 0.98. I go second enter to get that back. I change the L2 to L3. So L1, L3, I'm trying to beat 0.98. 0.99 beats it. Now I'm trying to beat 0.99. I do not know what just happened. Oh, somehow I went off my screen and hit a Microsoft Word document opening. Okay, so second enter, one more time, go get my L4. Trying to beat 0.99. And we did. Okay, that means it is the third graph right here. That's the winner, so therefore it's second order. So second order, since the graph of reciprocal concentration, molarity, let's do concentration, that was the word they used, versus time was linear. What is the value of the rate constant? Specify its units. We just said this is second order overall. So 2 fingers up for second order overall. So 1 molarity in the denominator, drop a finger, and the time is minutes. So I know that the units for K are going to be molarity to the -1, minutes to the -1. But let's get its value by looking over here on this handy dandy calculator. The K value is equal to the slope, absolute value of it, which is 776, which is plenty of sig figs. And it's not even times anything weird. It's just 776. Molarity to the -1, minute to the -1, which you could have written 776 over molarity dot minute. It's your choice. There's lots of different ways to communicate that correctly. So we got that done. Now calculate the number of minutes it takes. So you think to yourself and you go, minutes, that's a time. So that is an X value. And it takes for the absorbance to drop from 0.330 to 0.096. Let's think about that for a second. How am I going to pull that off? Well, my 0.096 corresponds to a molarity. Remember, back up here, I was told to use concentration units. So really, they're trying to get me to give them the time when that happens and subtract, right? From 0.33. Oh, that's way all the way up here. Let me subtract all the way. So essentially all they're asking me for is to fill in that last question mark. So I need to understand that my quest really is to find out what is the time, not for the absorbance to drop, but calculate the number of minutes when the concentration is equal to 3.50 times 10 to the -5. Okay, this was a little bit rude, a little bit unnecessary, but that's what we're faced with doing. So I really need to graph this, and I need to think about what I was graphing. So it was L1, L4. So go set up a graph if you don't already have one set up, which is L1, L4, which I do have one set up, so that's good. So if I go zoom 9, not only are my points in there, albeit not many, but so is my regression line, which is what I'm going to use to calculate this with. And so I'm looking for reciprocal concentration in my Y. So I know the Y, I'm in search of X. So Y equals, when I know the Y, and it's 3.5 second EE to the -5 with the reciprocal thereof. And choose enter, choose graph. If you don't see the intersection, my little calculator's still working, don't see it, what are you going to do? Zoom out. Zoom 3 is out. Doesn't look like it changed. Hit enter. Now it's changed. Come on, intersection. There we go. Can only calculate what it can display. So second, calculate, intersect, enter. Just keep pounding enter until you actually get an intersection on there. There we go. So X equals 26.1. 26.10 seconds. Oh, minutes, sorry. Look back at my table. Minutes. So the time required then is 26.10 minutes. And we're done with that. Then calculate the half-life of the reaction. I know you want this to be hard. It just isn't. All you need to do is calculate the time it took for half of your original sample to go away. So we really need then to reread this and rewrite this as, what is the time when concentration equals the 12 times 10 to the negative 5 over 2, known as 6 times 10 to the negative 5. So come back to my y equals, because I know what y is. And instead of it being 3.5 down here, I'm going to put in 6.0 and just graph again. Let it pick up that change. There it goes. Notice it is in a different place. That's a good thing. So second trace, 5, pound, pound, pound. And the answer is 10.7 or 8. What do you figure? 10.8. 10.8 minutes. T 1/2 equals 10.8 minutes. Okay, we worked that pretty dang fast. The rest of the country would still be crunching stuff out algebraically and making lots of algebra errors. So that is a good workout of 6 Arrhenius problems, probably more than you needed. And if you have made it this far to the bitter end, I think I'm developing a bit of a fan club. I appreciate very much your diligence and your dedication to learning chemistry, and I hope that you are actually considering being a science major and joining the Geek Sisterhood or Brotherhood, whichever. No gender bias here. But until next time, study hard. Thanks so much.